it's okay to, we can start, we can wait for 2-3 minutes, depend, okay, whatever you want. So.
I think there are a few people, so we can start.
Okay.
It's a pleasure to have Daniel Greb from University of Essen, who will tell us about projective flatness over KLT spaces and uniformization of varieties with an anti-canonical divisor.
Yes, thanks a lot for the invitation and for the opportunity to give this talk here. It's really a pleasure to participate in this online seminar, this worldwide seminar. And yeah, so that's my title, and I'm going to start with some motivation coming from varieties of general type. So assume that you have a smooth variety of general type, and even assume that your canonical bundle is ample, so it's canonically polarized, and n is always the dimension of X. Then we have the famous Miyaoka-Yau inequality on the first and second Chern class of this variety, which I've written here. So it's n divided by 2 n plus 1 c1 squared times kx to the n minus 2 is less than or equal to c2 of x times kx to the n minus 2. And there are a lot of reasons for that, but let me list two of them. So the first one is that by the theorem of Kobayashi, this X has a Kähler-Einstein metric. And so you can use that metric in the tangent bundle to compute a representative of C1 and C2. And then the symmetries of the curvature tensor, because it's Kähler-Einstein metric, allows you to prove a corresponding inequality pointwise on the level of representing forms, and then you get this inequality by integration. The second reason, which is closer to what to the methods I'm going to use, is that the following bundle, the cotangent bundle, direct sum with the trivial line bundle, together with the natural Higgs field, which I'm not writing here, is stable with respect to the canonical polarization as a Higgs bundle. Yeah? So, and then this means by work of Simpson, for example, that it has a Hermitian Young-Mills metric, and then again you take this metric in this bundle and you compute the Chern classes and you get this inequality. There's also an algebraic proof by reduction to characteristic P. So let's go to the other end of the classification. This is what I'm mostly interested in this talk, and let X be a smooth Fano n-fold. So somehow in parallel, you expect a similar inequality, and the only change here is that you replace the canonical polarization with minus kx as a polarization, which is now the natural ample class. Yeah, and I call this inequality my sub f, so for Fano version of the Miyaoka-Yau inequality. Unfortunately, or interestingly, okay, I mean, I put I marked here this factor, which is going to be important in the following. Interestingly, counterexamples exist, and they're easy to construct. For example, you take the projectivization of this rank 2 vector bundle on P3, so that's a fourfold, and you compute these the relevant Chern classes intersection numbers, and okay, you get 800 and 296, and if you plug it into the formula with n equal 4, you see it's violated. And so you see, as in many other problems, in the Fano world, some condition is needed, and it has to do with semi-stability, some sort of semi-stability condition. So, okay, for example, you notice that for this X, the tangent bundle is not semi-stable because of this vibration. On the other hand, if X admits a Kähler-Einstein metric, then this inequality holds with essentially the same proof as in the case of varieties with ample canonical bundle. And moreover, since you have this pointwise, this is an integration of a pointwise inequality, you can see that in case of equality, you have to be on Pn. And that's the Chernoguyev theorem. So we are going to approach this problem of the question of when does the Miyaoka-Yau inequality hold by methods from sheaf theory, and there we have the following remarkable sort of prototypical result, which is the Bogomolov-Giesecke inequality. And that's one of the versions I put here. So if X is a smooth projective surface, or rather S, I would say, okay, X and S are the same, and you have an ample line bundle on S, and you have a locally free sheaf F, which is slope semi-stable with respect to this polarization and has rank R, then the following inequality holds. So the C2 of the endomorphism bundle is bigger than or equal to 0. And if you compute the C2 of this end of F, you see this combination of C2 and C1 squared. So this already looks promising compared to what we had before. And while this inequality can be proven nowadays with rather, I would say, standard algebra geometric methods, the second line here is much harder. So moreover, if you have equality in this inequality, then the endomorphism bundle of F is flat. Yeah, and flat means it's given by a representation, so not necessarily unitarily flat, but it's given by a representation of the fundamental group of your surface S. Yeah, and this remark, the second part is hard. It uses analysis, the theorem of Donaldson on the existence of a Hermite-Einstein metric in a polystable bundle. And then to go from polystable to semi-stable, you use further ideas of Simpson on differential graded categories. Okay, so in order to show you that semi-stability is very important for the second line to hold, let me give you two examples. The first one rather sort of easy and somehow like a toy example, and then a more geometric example, which will lead to the arguments that I will consider next. So let's look at the first example. So you look at P1, and you take the following rank 2 bundle. It's O of -1 direct sum O of 1. So it's rank 2, and it's not semi-stable because the degree is 0, but it has this, the second summand obviously has degree 1, so it has bigger degree than 0, so it's not semi-stable. But the first Chern class is, the degree is of course 0, and the second Chern class is trivially 0 because we're on a curve. Yeah, there is no second Chern class. And so if I take X to be P1 times P1 and Q1 of the projections, then I can pull back this sheaf to, or this bundle to P1 times P1. That's still not semi-stable with respect to the natural polarization coming from the two O1s. But of course, the Chern classes are still 0. Yeah, so they're the pullbacks, so they're still 0. And this P1 times P1 has a trivial fundamental group, but the end of F is not flat, and F is also not flat. So really, this statement about in the Bogomolov-Giesecke inequality, the second statement is a statement about semi-stable sheaves with vanishing C2 and C1. F needed to be flat if it were semi-stable, but it's not semi-stable. Okay, so that's a rather artificial example maybe, but it still shows that semi-stability plays a role. A more geometric example in this Fano world is the following. Look at Y, the weighted projective space with weights 1, 1, 1, 3. So it's C4 minus the origin modulo C star, where the C star acts with weight 1, 1, 1, and then on the fourth coordinate with weight 3, has one isolated singularity, a cyclic quotient singularity. And then you take X to be a hyperplane section in some embedding of this, this weighted projective space. Yeah, for example, you can realize this weighted projective space as a cone over degree 3 Veronese of P2. And then you take this hyperplane section, and then you restrict the tangent of the tangent sheaf of the bigger, of this cone to the smooth hyperplane section. Yeah, and if you compute this, this delta, yeah, so delta is this combination mentioned of Chern classes mentioned in the Giesecke-Bogomolov inequality. Yeah, so 2RC2 minus r minus 1 c1 squared. This is called delta of the sheaf. This is 0, you compute that, but the endomorphism of this restricted sheaves is not flat. I'm not claiming that this is obvious to see. Rather, it follows from what I will tell you next. Yeah, it follows from our geometric considerations in the Fano setup, which I will move to now. Okay. So I'm working, if not stated otherwise, in the following setup. So X will always be a Q-Fano n-fold. So it means that X is normal, projective, n-dimensional. It has at worst KLT, Kawamata log terminal singularities, and minus Kx is Q-ample, meaning that, KLT in particular means that the canonical divisor is Q Cartier, and so minus Kx is Q Cartier, and then it's some multiple is Cartier and ample. That means Q ample. And so from the fact that counterexamples to the Miao-Kayao inequality in the Fano world exist, the question arises, what is the correct semi-stability condition for it to hold? So what can we impose? And what is reasonable to impose? Yeah, and okay, I inserted this this previous slide about Bogomolov-Giesecker inequality. This is an inequality about sheaves, and I stated or said that okay, it already looks promising and similar to the Miao-Kayao. So let's first try to impose semi-stability on the tangent sheaf. Yeah, so assume that the tangent sheaf is a slope semi-stable with respect to minus kx, which is the natural polarization here. And then you have the following proposition. Okay, it's written in one of my papers with Kebekus and Peternel, but it really goes back to, say, an idea of Kawamata. So under this semi-stability assumption, you have the following inequality, which I will analyze now and comment on on the right-hand side of this slide. Yeah? So first, what do the expressions mean? So you see that I'm having have this C1 hat and C2 hat here, and this hat denotes orbifold Chern classes. Yeah. So why do I have to deal with orbifold Chern classes here? Well, so this intersection number C1 hat squared times minus kx to the n minus 2 or C2 hat times minus kx to the n minus 2, how can I compute them? Well, this is the orbifold Chern class of the restriction of, say, the tangent sheaf or omega 1. This is the dual of Tx, the restriction of that to S, where S is a complete intersection surface for this polarization minus kx. Yeah, so minus kx to the n minus 2 means you take a n minus 2 general elements, say in some multiple, and you produce a surface, a complete intersection surface, and a general one, and you restrict the sheaf. So now, since you're dealing with Kawamata log terminal singularities, this will be a surface which is not smooth, but it has only at worst quotient singularities. Yeah, and that sheaf you see there, this Tx or omega 1 restricted to this surface with quotient singularities, is then an orbifold bundle, and that's why orbifold Chern classes occur. If you restrict to the case of terminal singularities or singularities which lie in codimension 3 or higher, this complete intersection surface will be smooth, and then you can write a standard C1 and a standard C2. And so why this is not a theorem, just a proposition or an observation. Basically, this is just the Bogomolov-Giesecker inequality for the restricted sheaf Tx or omega 1 of x. So why why do I write these two things? Well, you see, the Bogomolov-Giesecker inequality is a statement about the endomorphism sheaf. Yeah, so and this means I can really work with Tx or omega 1 of x. One is semi-stable if and only if the other one is semi-stable. So this is why I will sometimes switch between the two, because I couldn't force myself to be consistent. Yeah, so this is just an observation. And why are we not done? Which, if you look at this factor, Yeah, so n minus 1 divided by 2n, and you compare it with the Miyaoka-Yao, so the thing you want, which has n divided by 2n plus 1, then you see that it differs by 1 here and then here. Yeah, so this means that it's not as good as an inequality as the Miyaoka-Yao one. So I say it's off by 1 rank from the Miyaoka-Yao in the sense that the Miyaoka-Yao looks like the Bogomolov-Giesitka inequality for a rank n plus 1 sheaf. And this rank n plus 1 sheaf, we wanted to have the same Chern classes as the tangent sheaf. Yeah, so that's what you realize. It's a small observation, but it's an observation that you're not looking at the tangent has the wrong rank. It's rank n, and you want something of rank n plus 1 optimally. Yeah, so the question arises, what is the natural rank n plus 1 sheaf to consider in this problem? Yeah, and really somehow, okay, I always say this when I talk about this, it's that it is embarrassing that we only have this result now because we've been dealing with these uniformization problems for a long time now. We've been proving things in this direction, uniformization theorems, for far too long. But we always thought that the Fano case would be much more difficult than what we found here, because of course, we have all this theory of K semi-stability. We expected it to play a role, and also we were expecting certain characterizations of Pn in terms of rational curves to play a role. But eventually, it all comes down to considering the correct n plus 1 sheaves, as I will explain now. And even more embarrassing, this sheaf, which I'm going to present here, is not a new idea. It's been around for a while and has been used for similar problems. So what is the sheaf to consider? This is what we call the canonical extension. So again, the setup is X is a Q-Fano, dimension of X is n. So as I said, XKLT in particular implies that Kx or minus Kx is Q-Cartier divisor. So this means that some multiple is Cartier. Okay, I'm missing a minus here. So D should be minus m times Kx. So some multiple of it is a Cartier divisor. And so this means that Ox of D is locally free with some transition functions. And so using these transition functions, I'm now going to define a first Chern class on this singular space in the following cohomology group. Yeah, so I can take these transition functions, which are nowhere vanishing, and then do a d log of them. Yeah, so this means I do d of g alpha beta, and I divide by g alpha beta. And this is a Čech cocycle on discovering u, and then this gives me a cohomology class in h1x, omega 1 of x, and I call this the first Chern class of D. And so now I remember that D is m times minus kx, so I divide back by m. Yeah, so C1 of minus kx is 1 divided by m, this first Chern class, and it lies in h1x, omega 1 of x. Okay, so that's a very, very natural object associated to the canonical polarization, which is in this business, so rather the anti-canonical polarization. Okay, and now I make another small observation, because if you approach cohomology from the point of view not of Čech cohomology, but say of derived functors, you learn relatively quickly say coming from your homological algebra course that this h1x, omega 1 of x is an X group. Yeah, so h1 is the same as x1 ox, dot. Yeah, so there is this isomorphism, and so I have this element c1 of minus kx, and so this means that using this element, this first Chern class, defines an extension of what kind? Well, it's an extension of OX by omega 1 of x. So it looks like this. So since we are on a singular space and we're dealing with vector bundles, one has to be a little bit careful because we want to extract some further information. So you make the following observation. So if I take an affine open set U in X, then of course the cohomology of so H1 of U with values in any coherent sheaf, in particular omega 1 of X, vanishes. Yeah, so this means that the corresponding extension, which was constructed from an element in H1X, omega 1 of X, this will, the corresponding X class will be 0 on U, so the extension will split on U, and so this means this extension is locally split. Okay, this is a small technical remark, but this allows me to take duals and still get an exact sequence. So I'm still allowed to write zeros, left and on the right. And then I get something in the middle, which is the dual of W, and which I call EX. And note that while this, this W is an extension of OX, which is a nice sheaf, but with this potentially quite horrible sheaf omega 1 on a singular space, this EX, since it's a dual and X is normal, this is reflexive. So it's a reflexive sheaf, which is very nice to work with and has some more geometric, you have more chances of doing geometric arguments and geometric constructions. Okay, and so this is the basic construction. And we call this EX the canonical extension, or sometimes we also call the actual extension, this exact sequence, the canonical extension. And as I said, this is not my invention or the invention of one of my co-authors. So this is joint work with Stefan Kebekus and Thomas Peternell. But this has been considered earlier by Atiyah. So if you look at this on the smooth, on the open smooth set of smooth points of your Fano, then this is just the Atiyah extension of the C star principal bundle associated with the anti-canonical bundle. So it has been considered by Donaldson, again in the smooth setup, to analyze the problem of finding optimal representatives, optimal Kähler metrics in a given Kähler class, because notice that this construction here has nothing to do with the fact that you're starting with the first Chern class of a line bundle of a Q-Cartier divisor. You can do it with a Kähler form. And then Tian has considered it exactly in the same setup that we do, I mean, in the smooth case, and in the connection with the question of stability properties of the tangent bundle and the existence of Kähler-Einstein metrics in a 1992 paper. And then I've written a paper with Michael Wong 1 or 2 years ago, where we analyzed this construction more generally on compact Kähler manifolds, where we find that it has a lot of connections to problems in Kähler geometry and complex geometry, and a lot of interesting questions are generated by looking at this extension. And I'm not going to talk about this here, but I'm just saying that it's very fundamental, and there is still a lot of work to do in this area. Okay, let's do an example.
Great, Daniel. When you say you considered it in general for compact Kähler, you mean not necessarily Fano?
No, right. So I just take, say, a Kähler class, and then I look at in H1 omega 1. And the interesting thing is that this extension, while I have no longer a line bundle, okay, because it's not it's just a Kähler class and not a line bundle, I still have this sheaf. This extension still exists.
Thank you.
Okay, thanks for the question. Yeah, so if you do it on known spaces, you get stuff you've been considering for a long time. Namely, for x equal to Pn, you get the Euler sequence. Yeah, so in particular, in this case, the canonical extension is a direct sum of O of 1s. So it's semi-stable, but not stable. It's polystable. Yeah. Okay, so this generalizes very classical things. And so really, the next proposition, I mean, I write it to show you some of the arguments, but okay, we engineered this extension for it to be true. Yeah? So that it says, let X be a terminal Q Fano. So I'm just restricting to the terminal case here, not to be forced to deal with orbifold Chern classes. There is a KLT version where you just put hats on everything, and you use different references from what I'm using in the proof here. And then the statement is, if the canonical extension is semi-stable with respect to the anti-canonical polarization, then the Miyaoka-Yau inequality, the Fano version, holds. Now, this is just always the same inequality. The proof is easy. After the observation that the Miyaoka-Yau holds, okay, you see, as I said, you intersect with minus kx to the n minus 2. This essentially means you restrict the sheaves. So in this case, you're dealing with to a surface. Yeah? And so you restrict to a complete intersection surface d1 intersected dn minus 2. dj is in m minus kx. And so then you notice that your ex is an extension of OX by TX. So it has the same Chern classes as TX, but it has rank n plus 1. Yeah, and so here in my situation, this extension, I mean, or rather this surface here, because I'm terminal, lies in the smooth part of my X. So S is smooth, and EX is locally free around S. So this EX is a vector bundle locally free sheaf on my surface, and it's been made such that the Miyaoka-Yau holds if and only if the discriminant, so the C2 of its endomorphism bundle, is bigger than or equal to 0. Okay, but now I'm assuming that EX is minus KX semi-stable, and I'm restricting to a complete intersection surface for the same polarization, namely minus KX. And so the theorem of Mehta-Ramanathan, or Flanner in this singular case, implies that if I assume semi-stability of EX, the restriction to this surface will be minus KX restricted to S semi-stable if my M is large enough. But I'm free to do that here. So then I have a semi-stable sheaf, namely EX restricted to S on this surface, and then the Bogomolov-Giesecke inequality says that the delta is bigger than or equal to 0. So you see, it's a very easy argument once you found the right object to look at. So let me next comment on the obvious question on the condition, namely, when is this? Okay, are there geometric situations in which this canonical extension is known to be semi-stable? And that's actually already very interesting in the smooth case. So even for X a smooth Fano, there is something to prove. And there we have the following. If X has a Kähler-Einstein metric, then of course you know that X is K semi-stable. It's even polystable. And from K semi-stability, actually by results of Chi Li on the greatest Ricci lower bound, you see that for xk semi-stable, the canonical extension is semi-stable with respect to the anti-canonical polarization. Yeah, so you have this chain of implications. And actually, none of this can be reversed. Okay, upstairs, this is okay, probably well known to many of you. And I will comment on the lower arrow here in a second. What is interesting, I think it's a really, really great theorem, that even in the singular case, this stays true. So if X is a Q-Fano, we have that in case you know that X has a singular Kähler-Einstein metric. I'm not discussing how you decide on that. That's a completely different business. Then a recent result by Stefan Druel, Henri Gunancia, and Mihai Paun tells you that this canonical extension sheaf is still semi-stable. Yeah, so that's great news. So actually, so up here, the implication, smooth case, X Kähler-Einstein implies that EX is minus KX semi-stable. That's exactly the one of the contents of Tian's paper, which I mentioned from 1992. So the singular version of Tian's result, Kähler-Einstein implies EX semi-stable, still holds. And let me comment on this, this counterexample for this arrow. So the counterexample here is provided by a very classical variety. You take a general hyperplane section of the Grassmannian 2,5 in its Plücker embedding P9. Yeah, and you can cut once with a linear section, or you can cut twice. And in both times you get a counterexample, namely you get a smooth Fano manifold where the canonical extension EX is semi-stable, but it's not K semi-stable. Okay, so this is really a bigger class of manifolds and varieties where this Miyaoka-Yau inequality holds, and it has, in some sense, not nothing, but it's certainly not equivalent to being Kähler-Einstein, this condition. Okay, so after you found the inequality, of course, you aim for proving or analyzing the case of equality. And actually, we can prove more than just in the Fano case. So let me state it in the general setup. So now here X is an n-dimensional projective KLT variety, and I'm no longer assuming that minus KX is ample, so Fano, but I'm allowing minus KX just to be Neff. So, and also I'm allowing more flexibility on the polarization, although it's not so clear whether in geometric situations this gives you more freedom. So if there exists some ample divisor H on X such that EX is semi-stable, and you have equality in the corresponding, say, Bogomolov-Giesecke inequality, or this Miyaoka-Yau type inequality, then X is of a very, very special form. So you have a uniformization result, namely X is isomorphic to U mod G, where U is either an abelian variety or Pn. So in particular, either Kx is trivial or minus Kx is ample. So you have nothing in between. And this G is a finite group which acts on U, and the action is free in codimension 1. So outside of a set of codimension 2, you have a free action, and then you have some singularities in codimension 2 and higher. So in particular, if X is Q-Fano, and if your polarization H is the anti-canonical polarization, then this equality here is just equality in the Miyaoka-Yau. Then you're looking at an X which is of the form Pn mod G. So this is in some sense a complete generalization of this result of Chen-Oguye, that if you have a smooth Fano which is Kähler-Einstein and has equality in the Miyaoka-Yau, then it's Pn. Here you assume this less strict semi-stability condition on EX, and still you have a characterization not of Pn because of the singularities, but of Pn mod, a finite group. Okay, and so you have some nice corollaries even in the smooth case. I mean, this was known by classification, and as you will see, the proof is not free of classification, but maybe a little bit more conceptual. And also the reason I put this here is because I want to show you that working with this extension, this canonical extension, is in some sense pretty easy, especially compared to the question of deciding whether something is K semi-stable or admits a Kähler-Einstein metric. So the statement is, if you have a smooth Fano threefold with Picard number 1, then the Miyawa-Kayao inequality holds with equality if and only if X is Pn. Yeah? And so for the proof, you only have to check, given theorem 2, that the canonical extension is minus kx semi-stable. Because then the equality case will give you x equal to Pn mod g, and then since your smooth x is smooth, the g is not there. Yeah, so we check this, and then you're on the Fano manifold with Picard number 1. So this means that there is some generator for the Picard group, and minus kx is in there, and so it's a multiple of the generator, and it's known that for threefolds that can only be the multiple 1, 2, 3, and 4. And you call this the index, this number, this multiple. So index 3 and 4 are classified. This is a theorem of Kobayashi Oci, which will reappear in this talk, which tells you that index 4 is exactly you're on P3, and index 3 you're on a quadric. And okay, then you know what the canonical extension is, and it's semi-stable. So index 1 and index 2 remain. So let's do index 1 as an example of the kind of arguments you want. Okay, so you know from an old result, or an old observation rather, by Miles Reed, that for Fano actually n-folds of Picard number 1, the tangent bundle is stable. So eventually, this is an observation which reduces this question to Bogomolov-Sommese vanishing, or which is really almost the same, Kodaira, Akizuki, Nakano vanishing. Yeah, so by some vanishing theorems, basic or fundamental vanishing theorems, the tangent bundle is stable. Okay, so next you want to show that Ex is semi-stable. Now, how do you do that? So you take a potentially destabilizing subsheaves S inside Ex in the middle. Of course, you now use the extension. And so the first argument you do is really just by looking at slopes, so degrees in an exact sequence. You show that the fact that Tx is stable implies that this S has to go into Tx. So S, if you compose this inclusion of S into Ex with the quotient, it's an inclusion. And so, since now by assumption, so suppose that Ex is not semi-stable, not stable even, then you take this mu, this slope of S has to be bigger than or equal to the slope of Ex, but then Tx is stable, so it has to be smaller than mu of Tx. But now you compute these slopes, and since you're on a Fano manifold with Picard number 1, you know that these slopes they have integer, of course they're rational numbers with integer numerators, and then you know what the denominators are, namely n plus 1 and n here, and then you see that there is no room just in the rational numbers for a number like mu of S. So it's a very easy argument. Okay, and then for index 2, we still have to use classification to prove this, but there the classification is very small. So index 2 Fano threefolds with Picard number 1, these are all hypersurfaces in some weighted projective spaces, essentially except this linear sections of Grassmannians, which we saw all earlier. And I mean, maybe there are 5 cases or 6, and you check it in these cases by using the fact that there are hypersurfaces in weighted projective spaces, and you use the standard sequences on projective spaces. So it's really very classical mathematics here. Okay, just to give you some feeling how this goes. Okay, so let me move on to give you a proof of this uniformization result. So let's recall it. We have an X with minus kx nef. We have a polarization for which this extension is semi-stable, and the inequality which holds is an equality. And we want to show it's of this very special kind. Okay. So the main theorem that goes into this has been proven in the first version by myself, Kebekus, and Peternel, maybe in 2014, and then 1 year later in the orbifold setup by Lu and Taji. And this is the following. So this is a flatness statement, which essentially is just a generalization of the flatness statement of Bogomolov-Giesecke to the higher dimensional singular setup. And here is what it says. So you take a projective KLT variety, as always. You take an ample divisor, and you have a semi-stable sheaf on X, F. So if you have equality, so it should read C1 hat square here, in the Bogomolov-Giesecke, then it's not necessarily flat, but almost. Namely, there is a finite quasi-étal Galois cover. So this means you have an X hat over X. You have a finite map, which is étal over the smooth locus of X, and then branches over the singularities of X. It's Galois, so there's a Galois group, such that not this end of F is flat, but you pull it back to via gamma, so gamma upper star of F. Okay, then because of singularities and in F and X, it's no longer necessarily reflexive. So you take the double dual to make it reflexive, and then you take the end. So this sheaf is locally free and flat. Yeah. So this I emphasize that a priori F is just reflexive, but then this associated sheaf on this cover is actually locally free, and it's not just locally free, it's flat. Yeah, so this means that it's given by a representation of the fundamental group. Yeah? So what does this mean? Maybe I can write this explicitly. Okay, I mentioned flatness earlier, but maybe it makes sense to write this. Yeah, so what does a flat sheaf G on X mean? This means that if it's of the following form. I go to the universal cover, X tilde of X. I have a representation, a row of the fundamental group, pi 1 of X goes to GL, okay, of the correct dimension. C, that's the rank of G. And then I act with the fundamental group on this product on the left with deck transformation for the universal cover, and on the right with the representation. Yeah, and then I take the quotient, and this here is a vector bundle, and this is isomorphic to G over X. Yeah, so this is a flat sheaf. This is what I mean by a flat sheaf. Okay, let's go back to here. So this in particular means this reflexive sheaf is locally free. So what does this mean in our setup? It means that under the assumption of theorem 2, yeah, so let's go back. So I have this canonical extension. It has this equality, which is somehow required here, because here my rank is n+1. This endomorphism of the pullback double dual is locally free. Yeah, and so now there is some small functoriality going on. In the case of F equal EX, the pullback under a quasi-étal map gives you the canonical extension upstairs. So the direct corollary is that the endomorphism sheaf of the canonical extension on the cover is locally free and flat. Okay, and now in order not to have too many decorations, I'm going to assume that X is equal to X hat. And if you look at my statement, of theorem 2, I now only have to prove that this x hat, or without loss of generality x, is an abelian variety or Pn, because then the Galois group will be G for gamma, and then x will be the quotient of this Pn, or the abelian variety. Okay, so the first observation is, again, an argument we've been running for some time, that under this assumption, x is smooth. So why? Okay, you know that the endomorphism of Ex is locally free. So let's remember what Ex is. It's this extension, which I write here, which is locally splittable. And then the endomorphism is locally free. So if I go to a small open, affine open, where this extension splits, so then Ex is a direct sum, and I take the end of this direct sum, I see that Tx is a direct summand of a locally free sheaf. So Tx is locally free, and then since x is KLT, it's an easy argument, in fact, by Duell to see that x is smooth. Yeah, so this is the Lippmann-Zariski conjecture, the positive solution of this conjecture for KLT spaces. So x is smooth. Okay, and now I'm going to complete the proof in the Fano case, not to be distracted by some technical details. So let's assume that x is Fano, and then my aim is to show that x is equal to Pn. Yeah? Okay, what do we know? We know that the endomorphism sheaf of Ex is flat, yeah, given by a representation, and then it's actually not too difficult to see that Ex itself has some property which is known as projective flatness. Yeah, so what does this mean? It means that the projectivization of E is given by a representation of the fundamental group into PGLn plus 1 in a similar way than as I explained before. Yeah, so this projectivization of Ex comes from a representation of the fundamental group. But then we are on a Fano manifold, and these are known to be simply connected. Yeah, so this pi1 of x is trivial, and so in particular the representation is trivial, and so this means that this p of Ex is the trivial Pn bundle. Yeah, so this means that p of Ex is the same as the projectivization of the trivial bundle of the same rank. Okay, so now you have two vector bundles of the same rank, which give you the same projectivization. So this implies that these two vector bundles differ by the twist of a line bundle. Okay, on the right-hand side, there was the trivial bundle, so Ex is isomorphic to a line bundle to, so n plus 1 copies of some line bundle on X. Okay. So now let's analyze this line bundle. I take determinants on both sides of this isomorphism. Okay, what is the determinant of Ex? I've used this, but if you remember that Ex is this extension, then you see that the determinant of Ex is the determinant here. So this is minus Kx, Ox minus Kx. And of course, the determinant on the right-hand side is L2 to the n plus first tensor power. Okay, so what does this mean? This means that, remember, we are on a Fano manifold. The n plus first tensor power of L is an ample bundle because minus Kx is ample. Yeah, so this means that L is ample, and this isomorphism gives me an equality of first Chern classes, namely C1 of X, which is the C1 of this sheaf, this line bundle, is the C1 of this, which is n plus 1 C1 of L. And so this means that you have a Fano manifold where the first Chern class is divisible. So it's n plus 1 times an ample C1. Yeah? And that's exactly the condition that the theorem of Kobayashi Oci needs to imply that X is equal to Pn. This theorem of Kobayashi Oci is really almost the first characterization of Pn, and it takes these two assumptions. Yeah? And then if you have these two assumptions, you control the via Riemann-Roch and the fact that you're on a Fano and some vanishing theorems, you control the Hilbert polynomial of your of this L, say, which in the end will be O of 1, and you show that this is base point free, this L, and gives an isomorphism to Pn. Okay, so this implies that my theorem is proven in the Fano case. Yeah, so and now let me go back. The abelian variety case really occurs in the following way. Under these assumptions, minus kx nef, you look at the Albanese map, and you see that really the stability of Ex implies that not just minus kx, but the tangent bundle has to be nef. And then you have some structure theorems for the Albanese of varieties with nef tangent bundle. And then, okay, there are fiber bundles over the Albanese. And then again, semi-stability implies that either you're isomorphic to the Albanese, which implies that you're an abelian variety, or that you're on the Fano, that you're one of the fibers which are Fano. Yeah, so this is how you obtain the second possibility. Okay, so let me close by explaining to you one thing I really like, namely the way to construct a lot of examples of such Fano manifolds satisfying equality in the Miyao-Okayao inequality. Namely, so this is related to non-abelian finite simple groups. And so the main point here is this condition that you have to act on the projective space with an action which is free outside a set of codimension or subvariety of codimension 2. So you have to exclude stabilizers in codimension 1. And so actually it occurs for any representation of a non-abelian finite simple group. Yeah, so take a non-abelian finite simple group. You take any representation, say from the atlas, and then you add the trivial representation, and then you projectivize. So this means you take this representation V and you complete it to a Pn equivariantly. Then automatically this action will be free in codimension 1. And so this implies the quotient will satisfy equality in the Miyao-Okayao, in the Fano version of Miyao-Okayao. So how do you prove this freeness in codimension 1? Actually, so you use the fact that G is simple and non-abelian sometimes. So these are easy group theoretic arguments. But then there is one point at which you have to exclude that this representation rho of your finite non-abelian simple group is generated by quasi-reflections. And there, okay, I don't know an abstract argument. I even asked people participating in the write-up of the proof of the classification of finite simple group for an abstract argument, and they didn't know. But you can exclude this case by looking at the classification of quasi-reflection groups, which is easier, and you see that there is no finite, no simple group among these, and then you have this nice result. And so let me close with this nice picture, which is the Fano plane. So this is P2 over F2, a finite geometry. If you take the automorphism group, the linear automorphism group of this P2, so this is GL3 F2, so of F2, which is the same as PSL2 F7, which is called L27 in this finite simple group business. And so this has a beautiful three-dimensional representation, which occurred in algebraic geometry many times. For example, this if you look at so this three-dimensional representation of L27, if you projectivize, so this is now a P2, this contains in an equivariant, stable L27 stable manner the Klein quartic. Yeah, and then the L27 acts on the Klein quartic, and it has, these are all the automorphisms of the Klein quartic, and that's the maximum number of automorphisms you can have on a quartic. Or you take the same representation, the three-dimensional representation, you notice that there is an invariant quartic form, and then you add a trivial representation, just as I did here, and then if you look at the zero set of this quartic, then this this will be a K3, which is one of the K3s on Mukai's list of K3s with maximal group of symplectic automorphisms. Yeah, so that's a lot of fun of playing with these examples. And let me close my talk here, and thank you very much for staying with me and for your attention and for allowing me to give this talk here. So thanks a lot.
Are there any questions for Daniel? If not, we can thank Daniel again.
Thanks.
Thank you for your talk, Daniel.
Okay, thanks.
It was very interesting.